As we say, let's kick this pig. So let's look at some examples of single mean hypothesis testing. We'll try and work through these, and you can let me know if they're crazy. So here's an activity. It's an old one I've been using a while. Let's say a drug company hears patient reports that bad breath might be a side effect of a drug. Previous research indicates that on average, people's breath stinkiness was a value of 60 on some sort of standardized bad breath scale, with higher values meaning worse breath, and that the population standard deviation was 17.5. Now we're going to use that population standard deviation as a cheap trick so that we can keep using z-scores instead of having to use t-scores right now for educational purposes. And every once in a while that happens in the real world. You use a known population standard deviation, even though the population isn't exactly the same, because there are some circumstances where you can think the means might be different, but there's no reason to expect the standard deviations to be different. Anyway, a little dumb trick we're doing so that we don't have to dive into t-scores yet. So the question is, does the drug company, or does the drug significantly change people's breath on average? So with alpha 0.05. So what that translates into is, let's do a hypothesis test. Well, we could have done a confidence interval, but for right now, let's do a hypothesis test with an alpha of 0.05, and let's test this question. Let's find out whether it's plausible that the drug alters people's breath, whether that's a side effect. So here we have some data. Now you can follow along with me if you like. Those are the breath scale scores of a new study, where a very pathetically small study where the researchers are trying to answer this question of whether the drug alters people's breath. And here's the steps. Here are the steps that I recommend following. And you'll find 85 different versions of hypothesis testing steps, because it's a whole process. It's like saying, what are the steps for checking into your dorm room? You could divide it into 2 steps, or you could divide it into 25. It's a process, and I chose to divide it up this way. First, we'll write out our hypotheses, then we'll draw a diagram, we'll find the critical z-value we need to beat, for our observed value to beat, and then we'll calculate our z-observed value. We'll compare our observed z-value to the critical z-value, or you can just look up the p-value, and software just calculates p-value for you, and you just need to know how to interpret that. And then you make a decision about the null hypothesis, and finally you state your conclusion. So the technical part in the middle, finding the critical value and calculating z-observed, or finding the p-value, that's the meaty business, but the rest of this is just as important. So you can stop at any point and charge on ahead and see if you can get the answer, but let's look at these questions that I asked in the previous sample, or the previous slide, the previous presentation. What's your sample point estimate? It's 73.5. So that is our mean, 73.5. And what is the sampling distribution? All possible sample means of breath stinkiness of 10 individuals sampled at random from whatever the population is. I don't know what the population is. All possible consumers of the product, or something like that. I don't know. All humans? All adults? I'll leave that up to smarter people than me to decide. For this educational thing, we don't have to read too much about it. What's the mean of the sampling distribution? Well, previous research said 60. So we're going to say, is our drug returning a value significantly different from 60? What's the standard error? Well, we have this estimate from previous research of sigma, and so we're going to use our standard deviation from our previous research divided by the square root of n. So I'm going to put the little steps up there on the right. We need to write out and specify in words our null and alternative hypotheses. Our null hypothesis is probably something like the drug doesn't cause any change in breath smell on average, which we're saying it's a change, but in this particular case we can test this with a single mean instead of having to look at 2 means. Like, you could have just given people the drug, or measured people's breath before the drug and after the drug and measure the change. That would be slightly more complicated, and we'll learn about that later. But for this, we're going to say we'll just compare the after version of that, the after time period for these 10 people, to a known population value, and that will represent change from average, change from not taking the drug. The alternative hypothesis, I put HA here, sometimes I do H1, who knows. The drug does cause a change. In other words, there's going to be a difference. So writing these out in symbols, the true mean of breath stinkiness is equal to 60. That's the null hypothesis. The alternative hypothesis is that the true mean is not equal to 60. Now, why not equal instead of less than or greater than? I'll pause for a second here so you can answer that. Okay, I'll answer that question now. Because the question was phrased as, does the drug change breath stinkiness? Now, the company could be playing subtle, slight games to make things a little easier for them. And if you can, by say phrasing that way, things that way, and if you figure that out and tell me about it, who knows? It might be worth extra credit or something, because that's a good question. So a diagram might look something like this. I used R in a computer to make my diagram, but that's only because that was actually easier than figuring out how to sketch it and scan it and upload it. And this way my curve is very pretty. So here's the sampling distribution of the mean, sampling distribution of means. And so we have alpha is 0.05. And since it's a two-tailed test, because our null hypothesis or alternative hypothesis said not equal, we are willing to accept to reject the null hypothesis, we're willing to accept values that are not equal to this middle value, whatever the null hypothesis is. We haven't specified that. Well, yeah, we have. It's 60. I should have written that in there. Anyway, we're willing to accept values that are much higher than 60 or that are much lower than 60 coming from our sample. So we have two tails, and they're shaded slightly differently in this little application I have here. Now that we have that diagram, we should find the z-critical that we have to beat. Now, finding that z-critical is actually fairly easy. You just say alpha equals 0.05. We're looking at 0.05 and two tails. This is going to look fairly familiar to you. So 1.96. Or in R, you can use this little code. R does a lot of things more easily. But if you're going to use software, you can do the z-test or the t-test instantly. This is for educational purposes. So finding the critical z-value, we've done that. We can put it on our diagram because, of course, that's what cuts off the tails. So z-critical is the cutoff point. Our z-critical goes here and here, and they cut off the two tails. Now, from this z-critical on down and this z-critical on up, we call those the rejection regions sometimes, because if our sample mean falls in there, then we reject the null hypothesis, because those are far enough away from this middle value, the null hypothesis value, that we're okay with rejecting the null hypothesis if that's where our sample mean is. So now we calculate our z-observed. Calculating z-observed is pretty easy. You just take your sample mean, subtract the null hypothesis mean, and you divide it by the standard error of the mean, which is just standard deviation by the square root of n. So working that through, it's not too difficult. This is a z-value. I can tell you that's going to be statistically significant because that's a big fat z-value. You can tell that too. Why? Because you've already seen the critical z-value. But let's put them on the chart together. Here's our critical z-values there. And then we add our z-observed value of 2.44. It's way over here in the rejection region. It is farther away from the null hypothesis mean than either of the z-critical values. That's what we're doing. Now we could also represent that as a p-value. And we could say the p is less than the alpha. Alpha is the red shaded area, p is the green shaded area. But for a two-tailed test, you have to be sneaky and remember to shoot yourself in the foot with p a little bit. But it's okay. We know it's still significant. But if we want to get an accurate p-value, by the way, you don't care. A computer will do this. All you care is, did we reject the null hypothesis? Yes, we did. But if you wanted to calculate an accurate p-value, you'd have to calculate the p-value on the one side you found, which is the area beyond your observed value under the normal curve, and add that to the p-value on the opposite side of the normal curve. It's a silly detail. We're not going to do that in this class. It's just a detail to remember about two-tailed tests versus one-tailed tests. This was two-tailed. We were willing to look on both sides, so we've got to play it fair. We've got to calculate our alpha on both sides and split it in half, and our p-value has to be on both sides as well. But like I said, you don't need to worry about that. You just say, my z-value is in the rejection region, and you can basically stop at this point right here. You can say z is here, we're done. We reject the null hypothesis. Anyway, as I just gave away, what's your decision? Reject the null hypothesis. Because you can express this a lot of ways. Sometimes people try to write it in a single mathematical line. So the absolute value of the z observed is greater than the absolute value of z critical. And I don't have to add in the right direction for a non-directional test, because in any direction it works. But if we have a directional test, then you have to pay attention to not only whether the absolute value is greater, but is it on the right side of the mean? I mean, the right or the left, the correct side of the mean. Another way to say that is z observed falls in the rejection region. Another way to say that is p is less than alpha. So that green area was less than the red area. There you go. These are all reasons why you could say I reject the null hypothesis. So rejecting the null hypothesis is sort of the technical mathematical thing you concluded, but the conclusion for your study might be something like, the new drug does statistically significantly increase breath stinkiness in those who use it. And you always have, after this statement you make, you use that phrase statistically significant in there, which means we did a hypothesis test and got a p-value, or at least we could have gotten a p-value. We looked up the z or something. We did a hypothesis test. And then after that phrase, you always put something in parentheses, and there are very specific forms that are okay to do this, and you report the statistic and the p-value usually. Sometimes you have to report some extra information as well, but not right now. So there's one example. Now I'm going to dive into one more example, and then this video will be over, I believe. What if we don't know the population standard deviation? So what if real life, right? We never know the population standard deviation, really. I mean, we do sometimes. It's just rare. We rarely know it. But we have to use a hypothesis testing procedure. In that case, we have to use the t distribution. The t distribution, you can read about it in your book. It's a lot like the normal distribution. It's based on the normal distribution, but it's shaped slightly differently, and you can't use normal distribution tables to look things up. It was developed by a guy who was trying to quality test beer, so it has a beer history to it, and so it's kind of nice that way. So let's go through this again. Drug company, here's patient reports that bad breath, etc., etc. So now we change it a little bit. We have the previous research, we have the population value of 60, but we don't know what the population standard deviation is. We have the same setup though. So here's our data. Now what do we have instead? We don't have a population standard deviation, but we have a sample standard deviation. And we're going to use t all the way through, not z. Now, using t is pretty easy. You just have to use a different table, and you have to remember that you're using t. You change all your z's to t's in your papers and things like that, and your PowerPoint slides. So walking through, we take our inventory again. Our sample point estimate is the same. Sampling distribution of the mean is the same. Although we have to remember that the distribution we use, even though maybe in the population it's a normal distribution, it's not really normal. That the one we use is not truly normal because of our uncertainty about the standard deviation. What's the mean of that distribution? It's the standard error. Or sorry, it's the null hypothesis mean, and the standard error is this different standard error. We take our sample standard deviation, not because we don't have a population standard deviation, and we divide it by the square root of n minus 1. Not just n, but n minus 1. Other than that, this is pretty much the same. Well, and looking things up in a different table. So we write our null hypothesis and our alternative hypothesis. It's the same as before. And we draw our diagram, which is the same as before, but it's a good idea to write t and the number of degrees of freedom. The way the t distribution works is actually there's an infinite number of t distributions, although only the first 100 or so matter. A t distribution, there's a different one for each degrees of freedom. Degrees of freedom is n minus 1. And we can talk about that a little more in other lectures or in class perhaps, but you just need to know that when you're using the t distribution, you have to look up not just your value, but you have to look it up in the right distribution. And so that means you need to specify the degrees of freedom. So this is a distribution of t for 9 degrees of freedom. That's what that's going to be. But otherwise, the diagram looks pretty much the same. It's probably kind of inaccurate because I just reused a normal distribution curve, but it doesn't matter. T and normal look pretty similar to each other. So for your little hand-drawn sketches, don't worry about trying to make them different. Now here's another difference. We use the t table. The t table is confusing because you have to look up a whole bunch of values at once in one table. So in this case, we're going to look at degrees of freedom, 9 degrees of freedom, right here. And every t-table is a little bit different, but this t-table, you can look at one tail or two tails. We want in two tails 0.05 of the distribution, or in one tail 0.025 of the distribution, so that column. It's the same thing. One tail has 2.5%. That means two tails, if we were to use this twice, would have 5%. So that's our value there. 9 degrees of freedom, 0.025 and two tails. That's our critical t-value. Notice that it's a lot bigger than the other one. The z-value was 1.96. This is 2.26. You're always punished for not knowing things in statistics. In R, you can get that pretty quickly without looking at a table, as long as you remember this fancy little code, QT. It's kind of nice. So we can plot that critical t-value on our diagram. The critical value of t or z or whatever is what cuts off the alpha region. So it is the dividing line for alpha. So we have two alpha areas, two rejection regions, and so t goes in two places and divides those from the rest of everything. So let's calculate t. Notice how it's exactly the same as calculating z, except the standard error is calculated with n-1 and using the sample standard deviation instead of n and using the population standard deviation. Otherwise, same. So there's no real extra complication in calculating. Now the t-value we find is 2.16. This is going to be a different story, perhaps. There's our 2.16. Is it in the rejection region? Think about it. Okay, if it's not too obvious and I'm not insulting you, but think about it. Some of you have figured this out, some of you haven't. It is not in the rejection region. We are not going to reject the null hypothesis. T observed is too close to the population mean. It should be out here somewhere, but it is not. Another way to say that is our p-value is greater than our alpha value. So p is greater than 0.05. In other words, the overall probability of finding a sample mean this far away from the mean or farther is too high. It's greater than 5%. That's another way to determine whether we reject the null hypothesis. You can just look and compare t observed to t critical, or you can get a p-value. Computers like to give you p-values, but by hand we usually do the t critical, t observed thing. So we fail to reject the null hypothesis. When we can say the absolute value of t observed is less than the absolute value of t critical. We can say t observed does not fall in the rejection region, or we can say p is greater than alpha. Any one of those things is equivalent, although we would usually only use the first and the third one technically, and it's just standard to use this format whenever we're writing reports. P is greater than, and you'd write in 0.05. P is greater than 0.05. And then we state the conclusion. The evidence does not suggest that the new drug statistically significantly increases breath stinkiness in those who use it. So with the next lecture, we're going to talk about the situation of two means, of testing two sample means at once. And with that lecture, it gets slightly more complicated, but we'll try and keep our complications coming a piece at a time.